All right, so when current flows through a wire, a magnetic field appears around the wire. We saw that in the last thing.
Sorry about all that.
No, you know. This is your classroom,
Yeah.
girl. So, and we saw that. Hello, what did I do? I moved it. There it is.
Yep.
And the strength of the magnetic field depends directly, actually it should, varies directly with the current and inversely with the distance. So if we have we had the compass over the wire, and what determines how strong the magnetic field is around the wire depends on how much current you got flowing, how far away from the wire. Let's say this is a wire right here. Say we got the current going in, and the direction of the magnetic field is the right, let's say it's conventional current, is going to be clockwise here. So we got like this. However, farther out,
Not strong.
it won't be as strong. And if you run more current through it, you get a more magnetic field. Okay, here is the equation that governs this. Now, the B is the symbol for the magnetic field, and let me just write this over here. That's the permeability of free space, current over 2 pi. Guess why pi is here?
It's a circle.
Yep.
Oh, don't forget your R.
Thank you, dear.
It's just like, it's exactly like before, but with the permeability of free space plus a circle, plus identifying it's a circle.
Yep. And the magnetic field, the units are Teslas.
And Tesla is that, okay.
Tesla is a Newton per amp meter. And we'll get more into that as we go along. And it's 4 pi times 10 to the negative 7 Tesla meters per ampere. And you can see how that's the inverse of this.
Yeah. And so the goal is just to get the meters and the amperes.
Well, it tells you you can't use centimeters and you can't use milliamps. You got to have meters and amperes. So let's say the current in this wire is 0.125 amps, and that this distance right here is 0.01 meters. That's going to be 4 pi times 10 to the negative 7 Tesla meters per ampere times 0.125 amp, 0.125 amps, and I notice right away that these cancel.
Times
Divided by 2 pi and 0.01 meters.
Should we want to plug it in, we could.
And I'm looking at this, and this meter cancels this meter.
And it's Tesla's.
This pi cancels this pi.
Oh, the pies cancel. That's nice.
And I'm going to have
2
times 10 to the negative 7. 2 times 10 to the negative 7 times 0.125 divided by 0.01. That's 2.5 times 10 to the negative 6 Teslas. So the intensity of the magnetic field here is, I'm looking up the television because that's where I usually have it, 2.5 times 10 to the negative 6.
You don't want to put your answer on the next slide or whatever?
Pardon?
You don't want to put your answer on the next slide? Is that what you mean?
No, usually I have the television up here and the calculator's connected to the television. So I'm used to looking up there.
Yeah.
All right, well, let's say that this is 0.02 meters away. The only thing I have to do is change this.
And it's going to be a smaller number there.
How much smaller?
How much smaller? Twice as small?
I agree. 1.25 times 10 to the 6.
Mwahaha.
1.25. All right, so I don't want to do too much about this.
Nice when there's no squares involved.
Yeah.
Easier, just easier to you know, half small.
Yeah.
Okay.
All right, so two parallel current carrying wires will both have a magnetic field around them. Okay. So here, the conventional current is up, and the field you can see is going around like this. Here, the conventional current is going up, and the field is going like this. So that means the field due to this one is going in, and the field due to this one is coming out. What kind of force do we get when we have
Opposites
fields in
attract.
opposite direction?
So attraction.
You're going to have attraction. And you can see that right away. The wires experience a force because their magnetic fields interact. And so here's the one where you've got them going in one direction. Oh, no, here they're going in the same direction. In those two wires we saw, I had them going in the same direction. The kind of attraction depends on the interaction of the fields. So if they're both going here, they've got it going out. So here it's in the middle where they're going to interact, it's down. And here in the middle where they're going to interact is up.
Oh, okay.
And so they're in the same direction. It's going to be an attraction.
Wait,
you
wait.
see the forces.
Didn't
here.
you say that this one was down and this one was up?
Yeah.
How come they're the same?
Okay. So
Oh, you mean
this
the
one is
currents?
down, this one is up. So if you've got a down and an up for the magnetic fields, what kind of force? They're in opposite direction. We're not talking about the current here.
Yeah.
It's the magnetic fields that interact.
So they're opposite directions, right?
So they,
So wait, how come this one's the same direction?
because the current is in the same direction.
Oh, okay. So
That's a
good.
you know, that's an excellent point. That's a source of confusion.
Yeah.
So if the current is in the same direction, then the magnetic field between the wires are in opposite direction. That's attraction.
I see.
If the currents are in the opposite direction, here it's coming out and it's down. Here it's going in and it's down.
Oh, now they're both in the same direction, so it's repulsion.
Yeah. And so this is like the iron filings.
Yeah.
So they're going out, and here they're connecting together.
Okay.
So this is down, and this is down. So the B is opposite. That's attract, and this is repel because they're in the same direction.
Sweet. That makes sense. I was like, wow, why does it say opposite then?
Yeah, there's it's multitasking required
Yeah,
here because
yeah.
there's two things going on. So here's the bottom line. Current in the opposite direction produces interacting fields in the same direction.
Repulsion.
And
Okay.
that's repulsion. And so that forces the wires apart. Current in the same direction produces interacting fields in the opposite direction. This is what we saw in the
Yeah.
first one.
Yeah.
Here it's like this and like this. All right, so that's attraction. And the motor effect, and this is an external magnetic field exerts a force on a current carrying wire. So this is the motor effect.
Okay.
So I've got a magnetic field, a strong magnetic field here, and the direction of the field is out of the north into the south. So the field is that way, and I have negative.
Wait,
on
if this is north, wouldn't this be the south then?
No,
Okay.
it comes because if I
Oh,
put
you're right.
Here the deal is
Here's
the
this is
compass
the
will
north
tell the
side.
direction.
Yeah, this is the north side of right here. I got you. Okay.
Just make sure I got this right. Yeah, so the south end of the compass is attracted to the north end of the compass is attracted to the south.
Sense.
The definition of the direction of the magnetic field, hello. Oh man, I think we just, is out of the north and into the south. Now,
Did we
hold on
screw
a
up
second.
with it?
Hold on just a second here. Shit. You didn't record that, did you? Well, remember these?
Don't worry, it's just for me.
Trying to get these apart.
Yeah, it's ridiculous. Super strength.
Come on. All right. And this will happen in front of students.
Tricky little sucker.
Come on.
And they're like, Mr. Boykin, let me do it. Let me do it.
All right. So that's the north end.
Mm-hmm.
Wait a minute, that's the north end too. I got it flipped around. Okay, that's the south end.
Mm-hmm. There we go. There we go. Okay.
That's the north end. Okay, now what I've done here, of course,
I'm like, don't put my hands in there.
is I've screwed up the wire. So at any rate, let me see if I can get the wire back where it belongs. I know what I'm going to do. I'm going to do this. Like this. And like this. All right.
Ta-da.
So let me put these papers here so you can see the wire. All right,
Oh,
so
good,
the
nice.
direction of the magnetic field is out from the north and into the south.
Yeah.
And I've got the negative sides here and the positive side here, so conventional current will be running down.
Wait, say that one more time, Boykin. Sorry.
Conventional current goes out of the positive into the negative.
Oh, I see. Out of the positive and the negative.
Out of the positive into the negative.
So current is that way.
Watch what the wire does.
Ha.
Okay, it went over to that side, but it went to the outside.
Uh-huh. Oh, okay.
Okay, now I'm going to turn this around.
Now it's going this way.
Now I'm going to change the direction of the current.
And ideally it'll be going out. It'll go.
And now it's coming this way.
Oh, I see. Okay.
See, before it went to the outside.
So now it's it's going on the outside here, whereas this way it was going
Don't do
outside.
that. It's not this. It's this.
Oh.
So let me do that again. It's not this. It's this, and we'll get to that in a minute.
Okay. So what is so the question is, why is it going this on this side and why is it going on that side for the other one? That's
So
the main idea.
force is that way or that way. All right, so that's called the motor effect. And here here's an example, out of the north into the south. And here the current is going that way, and here the force is down. And so if I put my fingers in the direction of the field, which is that way, and my thumb in the direction of the current, which is that way, if I slap somebody, I'm going to deliver a blow with the open palm of my hand if I slap that sucker.
So force is direction of the palm.
Here,
or your finger
here's
pointing.
the right hand roll is an open hand. The fingers point in the direction of the field. Okay, the fingers point in the direction of the field, and the field is in this way. Okay, the thumb points in the direction of the current. So
The
first time we had it like this. We had the negative down, so it was down. So the field of this.
And the force
Wait a
was
minute,
that.
let's see here. I got the negative here.
The first time I think you did out of the positive, right?
Let's just try it out. So if the bottom is negative and the top is positive, what's the direction of the current?
Going like this down, conventional
So it's
current.
down. And so I predict then that the field is this way, the current is down, that it'll end up on that side of the magnet.
Oh, I see. Okay.
No. Okay, positive. Okay, positive. Oh, wrong. Positive end. We're talking about electrons. The positive end. Yeah. Yeah, the positive end is this.
Oh, the positive and the negative. Try flipping it. Let's see what happens when you flip it.
Not much because it's stuck.
Huh, okay, so
You know,
we must be saying we must have messed up with the
and
magnets here.
These are too far apart, and I'm going to have to. Very carefully move these and get this out like that. Yep, it went this way.
Okay, yeah, and that was the...
Okay, so the field is that way, the current is down, the force is this way.
pushing it that way.
Yeah. The
Gotcha,
palm
gotcha.
points in the direction of the force. That's the third right-hand rule. First right-hand rule, second right-hand rule, third right-hand rule.
Gotcha.
Like this.
Yeah, I kind of like it with just like doing the palm because sometimes I'm like, which
Because when
one?
you
Like,
slap a sucker,
Yeah.
you deliver a blow with a palm of your hand.
yeah, because I'm like kind of like, wait, which one is which? The palm just makes it easy to think about.
All right, so here we've got a magnetic field going from left to right.
Yeah.
And here we have a current that's going in. All right, so we put this in the field, and so the direction.
Wait, how did you know that was going in, that current right there?
Well, there's a
X right there?
on there.
Okay.
And you can see the X better here.
Oh, okay, I see.
But you know what it is? It's
You know what it
double
is.
Click, expand it.
Yeah.
But you can tell by the direction of the field.
A current that's going into this field
Well, if
like
you
that.
don't know the direction of the current, but you know the direction of the field,
Yeah.
you can get the direction of the current. So at any rate,
Oh, true.
so fingers in the direction of the field,
Uh-huh.
thumb in the direction of the current.
So the force
will be down. Okay, so that means down. So let's take a look at the top. On the top, the field is in the same direction. The two fields are in the same direction.
Wait, let me orient myself here. Sorry. I see this has a north and a south right here.
See the blue?
Yep. Mm-hmm.
The blue is the magnetic field of the wire. Just ignore these.
Oh, okay.
Just look at the direction. So
Got it. Okay.
on top, the direction of the wire's field is to the right,
Okay.
and the direction of the bar's field is to the right. When they're both in the same direction, attraction or repulsion?
Repulsion.
Repulsion. Okay, and so down here on the bottom, underneath, the field due to the wire is to the left. The field due to the magnets is to the right. When the fields are in opposite direction, attraction or repulsion.
Attraction.
So we got repulsion on the top, attraction on the bottom. Force is going to pull it down. So we've got two ways of thinking about it. Visualize the fields. Same direction repel, opposite directions attract. Or you can use the right-hand rule. The direction of the field is to the right, fingers to the right. The direction of the current is in, so the force will be down.
So this is like the easy way to look at it, but you have to realize that when it actually gets put in the electric field, different things are happening in terms of the forces. You know, like, so, I mean, it's just a more descriptive way to look at it.
Well, what happens is fields interact with each other.
Yeah.
So here they are undisturbed.
Yeah.
And when they interact with each other, that's when forces are exerted. And you can kind of see it's almost like going to go boing.
Yeah, can you walk me through what you said one more time? So we've got the current is going in.
Okay, you want to do the hand thing or you want to do the field thing?
Do the field thing.
Okay, field thing. When fields are in the same direction, like the bar magnet like this,
Yep. Repel.
and see they're in the same direction.
Yep.
Okay. Here are the fields. The field due to this
Goes out to the north into the south, so they're in the same direction.
Yeah.
Oh, no.
Well,
Wait, hold on. Oh, no. When they're going opposite. This one's going this way, and these ones are going this way. I forget. Sorry.
no, it's good.
What did we say?
With the interaction of the fields. This is in this direction.
Current in the same direction. Oh, these are in opposite directions, right?
Yes, because one's going this way.
Yeah, exactly. Yeah.
And this one is...
Yes, that's right.
It's coming in, it's going out.
Same direction.
Here they're going in opposite directions.
Okay, and so as we look over here...
Hold on.
I'm looking at your
definition. Is that what we did?
I'm looking at your definition right here. If you can see that.
Fields are in the same direction, you get repulsion. And fields are in the opposite direction, you get attraction. Okay, let's go back to this here. We can't float by this.
Here you told me so down, up, opposite.
Oh, you know what? I remember.
Attraction.
Suddenly, I remember what I used to do. Okay, now, all right, because that's confusing. I used to do a north, south, north, south, out of the north into the south, out of the north into the south. Okay. When you have them set up like this, they're going
in the same
to,
direction.
Yeah. Did I pull a couple out?
They're
okay,
on.
no. So if you've got the like poles repel, like poles repel. What's the direction of the field? And then you got this north and south, and this south and north. Out of the north into the south, out of the north into the south.
Attraction. Okay.
So, and I did a thing where we played with the bar magnets. We did like this. We drew single things like this, because when you look at the ends, you get this weird thing that's happening.
Yeah.
But here, this is more analogous to this. They're in the same direction, repulsion. Here, the fields are in opposite directions, attraction. So let's go back to where we got confused.
Okay. So now we're here.
So here, the fields are in the same direction, repulsion. Fields are in opposite direction, attraction.
Okay, that's making sense.
Okay.
Challenge! Clip an alligator wire. Oh, sorry, Boykin.
That's not you, it's me.
Yikes. That's like,
So
that shouldn't be there
technically.
technically.
I'd have the kids do a problem. Okay, you guys do the problem, and I'll do it, and then I'd go under here.
Yeah, I know. That's why I love it. I'm like, don't ever take my projector
Do
from
the
me.
problem on the board.
Okay.
Okay, so first you got
So we got to clip an alligator wire at the end of each magnet wire, lay the magnet wire on the table.
Also, a little bit later, we will see what we're doing when we do this. Okay, so we have a north and a south, and we're through with this, and I'm taking it off. This, and if I lay the wire down like that, and
So you need the force to be, let's see, it needs to be up, right?
so this is north, this is south. The direction of the field is that way.
So the direction goes this way. You need the current to run that way.
Yeah, and so always looking for items to use. How about this?
And so we want to connect the, so, well, wait, so.
Which way do we want current to go?
We want.
So here I've got negative and positive. What direction do we want the current to go to have the force?
So it's all conventional currents. We want the positive in here and the negative in here.
Oh, is that what you want? So you want current flowing this way?
Yeah. Right? So then it lifts it up.
So this is the
North to south.
This is the north. So the field is this way. We want it to go up. So we want the current to go that way. So.
Yeah. And that's conventional current, right? That's how we're thinking about it?
Yep.
Okay. Oops. Wait, let's see.
Go ahead and bite it on.
We can do.
All right, so here we go. Well, it doesn't.
Yeah, no, it's going. We can see it. Let me see if I can tighten it here.
No, go ahead and take this off.
Oh, okay.
Put these. You want them as close together without touching as possible. All right.
Yeah, you can see it moving up.
All right, so success.
Success. Okay, that makes sense. Can you use the third right-hand rule?
Yeah.
Do you know which way current is going? Okay.
Yeah. All right, now, what about the left-hand rule? Left hand is for electrons. So electrons are going to leave the negative side, and the current is going to be this way. So your left hand...
It gives you the same result.
Yeah, gives you the same result.
Yeah.
All right.
Okay.
Make a diagram here. Set up, show I, show B. So I'll go ahead and do this. All right, so I'm going to do the wire. South. So let's have this. Okay, that's the bar magnets. And what we want is a force up. All right, so the field is that way. We want the force to be up. So we want the conventional current to be coming out, yes?
Make a diagram. Oh wait, is this what we just did?
This is what we just did.
Oh, okay. Technically, it's like out of
Here's the wire. And here's the north and here's the south. The magnetic field, the fingers of the field are
Oh
going
yeah,
this
okay,
way.
yeah, I see.
Okay, if we want the force to go up, we want the current, conventional current, to come out.
Yeah.
So I'm going to make a red dot here. So there's a conventional current out. Okay, what's the direction of the, this is, we'll call this B. What's the direction of B due to I? Well, it's coming out. So
I see. It would be, yep,
B
like that.
due to the current is going to be like that, yes?
Yes.
So, same direction, repel, opposite direction, attract. Explain how the third right-hand rule is at work. Well, the fingers show the direction of the field. Thumb shows the direction of the current. The direction of the force is the palm.
Okay.
Are we good?
Yeah. Now, the attraction part.
Okay, I did the attraction repulsion because of the two.
Yeah, those
fields
two.
here.
How do those play out in what we see?
It's two ways. Whoops, wrong.
I was like, well.
It's two ways of looking at it.
Okay.
Okay. Why are forces exerted? Because the fields are interacting. So here's an interaction of the field. Here's the interaction of the field. What's another way to remember that? Third right-hand rule. Third physics gang signs. Third right-hand rule. So what's going on is the fields interacting. That's where this attract repel comes from. But how do we get to this? How do we determine which way the current was going to go? Using the right-hand rule. So there's two ways of justifying or understanding or predicting what's going on. And okay. Now let's go. Okay, that's the old book.
Old book. Number 15.
16A. For each electro...
Don't forget number 15.
Number 15. Drawing shows an end-on view of 3 parallel wires that are perpendicular to the plane of the paper. In 2 of the wires, the current is directed into the paper, while the remaining wire current is directed out of the paper. The 2 outermost wires are held rigidly in place. Which way will the middle wire move? All right. So we've got, on the outside, it's, okay. The one on the left is in.
Yeah.
The one in the middle is in.
And the one that, out, in. There you go.
All
And
right.
then the current, in 2 of the wires, the current is
So
directed
these 2 are held steady.
to the paper.
This one's free to move.
Ah.
Which way will it go?
Oh, so we
All
look
right,
at
now
the B
here's
fields.
where, if you try to apply the right-hand rule, it's going to get confusing. But here, if it's going in, the magnetic field is this way.
Yep, same with that one. Opposites.
And if it's coming out, the
Same.
magnetic field is like this. Like this, yeah?
Yes.
So same direction,
Repel.
opposite direction.
Attract, yeah. So it's gonna move left.
Now, see why I teach them this thing about fields?
Yeah.
The whole thing about if they're in the opposite direction, they attract, if they're in the same direction. Because when you get to something like this, if you're doing the third right-hand rule, it gets confusing. It gets more challenging. But with the fields, see how clear it is?
Yeah, I like it. Yeah, because if you start thinking about that, it's just like, it gets kind of wonky. Okay.
Yeah. All right. 16A. For each electromagnet at the left of the drawing, explain whether it will attract or repel from the permanent magnet on the right. Okay. Well, which way is the current flowing? So it's coming up in the back. It's going down in the front.
Okay.
So that means the current goes up in the back, down in the front.
So our B field is that.
This is the north end. This is the south end.
Yeah.
Okay, the other one,
Wait, what's asking? Will it attract or it'll repel?
I don't care what the question is.
Oh, okay.
This is the bottom line. And the other one on the right, it's, oh, wait a minute.
Yeah, no, you had the first one right.
Okay, on this one, it's going down in the front and up in the back.
Yes. Down the front, up in the back. Oh. Wait, we can draw a little different. Hold on, like this. So
We're doing this one.
Yeah. So you drew them the same there. Start from.
No, check it out. It's coming up in the front. Oh, okay. Wait a minute. You're right.
This one right here is. Oh shit.
Up in the front.
We're good.
And then down like this, yes? Up in the front.
I can't tell what your errors are.
Okay, in the back, It's coming up, yes?
Yeah.
Wait a minute. So down here,
There we go. There we go. That's
And
right.
up
That's
here.
right. I'm like, I can't tell. Yep, that's right. That's right.
okay, so it's up in the back. That's going to be the same as this one.
Mm-hmm.
So this is north and this is south.
Okay.
So it's north on both ends. This is going to be repulsion. That's going to be repulsion.
Yeah. Okay. That's what I was thinking. Repulsion. Okay. And then 317.
All right, so I'm not going to make drawings here. For A, this one
Wait, for each electromagnetic.
It's the same thing.
Oh,
You're going to attract or repel.
Oh, okay.
Okay, so for this one, it's going up in the back and down in the front. So this is north.
Mm-hmm.
And it's the same thing over here. So that's going up in the back and down in the front.
So attraction.
So this is going to be a north. This is going to be a south. Here, it's up in the front, down in the back. So this is a north. That's a south. And then this is the same as what we had before. So that's going to be a south and a south. It's going to be repulsion.
Okay, that makes sense. Okay.
All right, where are we at here?
Oh.
Okay.
I might have clicked this. I don't know. I don't know this is what's like.
Oh, no, this is good. This is
Oh,
where we
right,
want
it's
to
okay.
go. Current carrying wires. This is a dot. That means it's coming toward us, right?
Mm-hmm. Yep. Bada boom.
This is an X, means it's going away from us.
Yep.
Kind of
What type of repulsion?
Yep. And so you can see what I'm doing with the students.
Yeah, lots of.
Repetition.
You kind of go to the hard stuff, and you come back to the easy stuff too. It's like, don't forget your fundamentals, people.
Well, and what it does is you have to work that way. You have to go back and forth. Basically it's circling around.
Yeah.
Force acting on a current wire in a magnetic field. Bill, not
a science guy.
All right, so the force exerted on the wire depends on three things: the intensity of the magnetic field, how much current's flowing to the wire, and how much wire is in the field.
Okay.
How much wire is actually in the field. In fact, here it is right here. So let me put Bill over here. All right. This is my second favorite equation. Bill, there's Ed, there's Bill. Of course, there's it. Okay, a straight wire carrying 5 amp current experiences 20 newtons of force when 0.10 meters of it runs through a magnetic field. What's the strength of B? Okay.
So we got 5 amps of current, 0.2 newtons of force.
Let's use
length,
this.
it runs through magnetic
Let's
field.
use this. Let's say, well, no, we're not going to use this. Here's a wire, and here's north, here's south, and we'll say I is equal to 5 amps. And the intensity of the magnetic field, I love teaching this stuff. I've forgotten how much, because it's fun to play with. You got the kids playing with stuff out of the north into the south. So this is B is, we don't know.
We don't know.
Okay, and the length, I should do this. The length from here to here is 0.10 meters. 0.10 meters. And it's going to, the field is down this, so the force
Is
purple.
into the wall.
Force is going to be in. Force
Yeah.
is in, is 0.2 newtons. just Bill.
Bill. But it's helpful to see how to draw
B
it.
is going to be equal to F over.
I thought it was going to be Phil.
It is, Phil.
Yeah. That's
All right,
funny.
so that's going to be 0.20 newtons divided by 5 amperes times 0.10 meters. That's 0.2 divided by 0.5. That's going to be 0.4. 2 divided by 5, 2/5 is 0.4.
2.4, yeah. 0.4. Or 4. No,
Well,
0.4. 0.4. Yeah.
0.4 Teslas. Now,
Tesla.
here's the deal.
Forgot that my units.
0.20 divided by parentheses 5 times 0.10, 0.4.
Nailed it.
Okay, so I've got newtons, ampere, meters,
That's Tesla.
which is a Tesla. Units of the field are
There it
Teslas, which is Newton over amp meters. And actually, this is the definition of electrical current. Let's see. I is equal to F over BF. The definition of an ampere, the SI unit, is newtons per Tesla meter.
Oh, interesting. It's not an ampere. It's
No.
all that.
Yeah, because what's an ampere? It's how many coulombs per second. How the hell do you measure coulomb?
Yeah.
You can't.
You can't. You don't really know.
No. And so,
But you can measure force.
so you can measure a force. You can know the strength of a magnetic field, and you can know the length of the wire inside of
It's
it.
got to be measurable.
This is the SI definition for.
Okay.
All right, here's the deal. If
Bill sine theta.
we have our wire that's perpendicular to the magnetic field, then there's a certain amount of force. If the wire is not perpendicular to the magnetic field, the amount of force is diminished. Okay, and so do I have a visual for this? I should have a visual for this, and I don't. Well, I don't have one that I want to share with you. Well, because and this is the way I am with my students. Okay.
Sorry.
Did I print this out? 2008 free response number 3.
And then page 663.
I did not. Oh, you know what? I got it back here. Well, I tell you what, open the book and look at that stuff.
So a wire carries a current of 0.66 amps. This wire makes an angle of 58 degrees. Yeah. Okay, so we're just gonna do force equals Bill sine theta L equals F over BI. For number 26, I think this is the equation you used.
Number 26. A wire carries, it gives you the current, gives you an angle with respect to magnetic field. The wire experiences a force. What's the length of wire?
Did it tell you the magnetic field?
Yes, it does.
Okay, yeah. Bada boom. Okay.
So I don't think we need to do that.
Nope.
27. Electric power line carries a current of 14,000 amps, 1,400 amps, in a location where the Earth's magnetic field, and this is a true thing, is 5 times 10 to the negative 5 teslas. The line makes an angle of 75 degrees, so that theta is 75 degrees with respect to the field, determined the magnitude of the magnetic force on 120, so it gives you the length. They want to know the force, it gives you the length.
So just do regular Bill sine theta.
Yeah.
Okay. All right.
And then 29, a wire coil. All right, let's take a look at this.
Number 29.
Yeah, this one we can't just...
Glaze. No glazing. I'm going to go ahead and read it. All right. 29 says, a square coil of wire containing a single turn is placed in a uniform magnetic field, as the drawing shows. Okay, so you've got this B. All right, each side has a length of that many meters, and the current in the coils is 12 amps to determine the magnitude of the magnetic force on each of the 4 sides. Okay.
Okay, here's the big deal. I don't care what the answer is. You got 4 sides. They want to know the total contribution. These are 90 degrees. Mm-hmm. This is 90 degrees, and these are 0 degrees. So
sine of 0.
Sine of 0 and sine of 90 degrees. Sine, hello, turn it on. Sine 0 is 0. And sine 90 is 1.
Perfect. So it's just Bill.
Yep.
Okay, so does it what numbers does it give you in there? It gives you the length of each side.
It gives you the length of each side. It gives you the magnetic field.
Okay.
And it gives you the current.
Okay, and it wants to know the force.
And the force is
what does it actually say for the words for the way it asks the
go
question?
ahead, read it.
Determine the magnitude of the magnetic force on each of the 4 sides. So it wants to know when you're looking at this, the current, which direction the current is. This direction, the B field. Oh wait.
So what that means. That's the length times the current times the strength of the magnetic field. This is going to be just Bill. Mm-hmm. These guys are going to be 0.
Yeah,
and why is that? Because the angle between the field
0.
and the length of wire is 0.
And so you just add these 2 up together.
Yeah.
Okay. Now, if you were to do the third right hand rule on this, how would you do it?
I wouldn't.
Oh, okay. Oh, okay. I see. The current is this way. I see. Okay.
It doesn't
it's
tell
not
you
important.
what the direction of the current is. Yeah.
Yeah, it's not important. Oh, I can't actually. It does.
Oh, it does.
I just don't know which is the current the purple or is it the?
So what they're asking for. Well, I is going to be clockwise.
Oh, okay, okay.
So that means
the current is this way in the B field.
Clockwise. So here, the force will be towards us.
And then for this and for the.
And then on the bottom.
So do you subtract?
So there'll be a twisting force.
So do you have to subtract your 2 answers?
Well, what are they asking for? They are determining the magnitude on each.
Oh,
not the
just
total.
separate.
They're not asking
okay,
for
okay.
the
So I really just didn't understand what the question was specifically asking. Okay, that makes sense.
So they want to know the sum.
Sweet.
All right, now look at this.
All right.
A rectangular wire loop is connected across a power supply with an internal resistance of that much and an EMF of 16 volts. The wire has a resistivity of that much and a cross-sectional area of that much. When the power supply is turned on, the current in the wire is 4 amps. Calculate the length of wire used to make the loop.
So if you want to find length.
And the answer is No, I'm not going to do that.
Okay,
Because resistivity, see, because what
oh yeah, resistivity. That has to do with the
yeah, the resistance R is equal to resistivity times the cross-sectional
area divided by the length, right? Okay, and you just switch out the L and the R, right?
Yeah, and does it give us the diameter of the wire?
Resistivity.
Cross-sectional area, yeah, so when the power flies. So then,
Is that all of the things involved in that? Yeah. Okay.
well, what you have then, this V is equal to IR. So R is equal to V over I, yes?
Yeah, yeah.
And they want you to solve for L.
Oh, okay. Oh, I see. They give you the voltage. They give you the voltage there.
And like I said, I'm not
They give
going
you
to
the
do it.
current. Nope, we don't do. Okay.
Because this is what's matter. The wire loop is then used in an experiment to measure the strength of the magnetic field between the poles of the magnet. We want to know what B is. The magnet is placed in a digital balance, and a wire loop is held fixed between the poles of the magnet as shown above. So the wire loop can't move, but this is on a balance scale. It can go up and down. So that's the length is inside the pole, so it's completely inside, and perpendicular to the direction that the power supply is turned on, so that the 4 amp current is directed below. Which direction is the force on the magnet due to the current in the wire segment? Well, the current is going in, yes?
Yeah, current this way, and we know we go north to south.
So here's the deal. You don't want to break your arm.
Yeah.
Move the paper.
Move the paper.
So,
Like this.
yeah, it's going to go down.
Go down, yeah.
So the force on the wire is down. The force on the magnetic field is up.
I see.
Right?
Yeah, that makes sense.
Because what's happening, the wire can't move, and what's producing the force? The interaction of the two fields.
Yeah, so this will go up. So it's just opposite of whatever the force
right.
on the wire is. Okay.
Okay.
So downward.
So the reading of the balance is changed by that much when the power supply calculates the strength of the magnetic field. So that's just built.
Built. So we got the force, and then you've got the B.
And they've got the length. There's the length. And they give you the current. It's 4 amps. And
It's just 90 degrees, so it's that doesn't matter.
Yeah, we're going to solve for B.
Okay, that makes sense.
All right, how are we going?
Good. I'm gonna pause this one.